Look up on a clear night, away from city light, and find the brightest point in the southern sky that isn't the moon. If you live far enough south, you'll see it, a steady, brilliant star sitting low near the constellation Centaurus. It looks like one star. It has looked like one star to every human being who has ever lived for the entire span of our species. It is not one star. It is three. And tonight, we're going to ask a question that sounds simple, but turns out to be one of the strangest thought experiments in modern astronomy. What would happen if Earth, exactly as it is, orbited that system instead of our Sun, not a similar planet, not a hypothetical Earth twin discovered by a telescope? This Earth, same mass, same ocean, same atmosphere, same moon trailing along behind it, lifted out of our solar system and set down in orbit around Alpha Centauri. At first, this seems like good news. Alpha Centauri A, the largest of the three stars, is almost a twin of our Sun, similar size, similar temperature, similar color. If you wanted to pick the most Sun-like star within reach of a spacecraft, this is the one astronomers point to first. So the planet should be fine, right? Here's the detail that changes everything. Alpha Centauri A is not alone. It has a partner star, Alpha Centauri B, locked in a slow gravitational dance that takes about 80 years to complete. And far out at the edge of the system, there is a third star, small and dim and famous for a single reason. It is, at this moment, the closest star to our Sun that is not our Sun. Proxima Centauri, 3 stars, 1 planet. And a question that astronomers, used to thinking about single-star systems like our own, don't get to answer very often. Could Earth survive there at all? To understand why that question is so much harder than it sounds, we have to start with something almost embarrassingly basic, something we never think about because we have simply never had to. We have to understand what it means, really means, for a planet to orbit one star instead of 2. Every model we have of how a stable planet works, the seasons, the calendar, the tides, the climate, assumes a single dominant source of gravity sitting at the center. Earth orbits the Sun in a path so close to a perfect circle that astronomers call it nearly circular, varying by only a few percent throughout the year. Nothing tugs hard enough on us to disrupt that. No other massive object is close enough to compete with the Sun's pull. This isn't a universal law of nature. It is, in many ways, a privilege. Our solar system has one star, carrying 99.8% of all the mass within it. Jupiter, the heaviest planet, is a rounding error by comparison. The result is a kind of gravitational monarchy. One ruler, and everything else following orderly, predictable, repeating paths. Earth's orbit has stayed close to its current shape for hundreds of millions of years. Stable enough for ice ages to come and go on a calm, almost gentle rhythm. Stable enough for complex life to evolve over unbroken stretches of geological time. Now picture removing that lone ruler and replacing it with 2 governments that both believe they're in charge. That is roughly what life around Alpha Centauri A would mean. Alpha Centauri A and Alpha Centauri B are both heavyweight stars by stellar standards. A is about 1.1 times the mass of our Sun. B is about 0.9 times its mass. Neither one is a junior partner. They are bound to each other, orbiting their shared center of gravity at a distance that, depending on where they are in their 80-year cycle, ranges from about 11 times the distance between the Sun and Earth, at closest approach to about 36 times that distance at their farthest. If Earth orbited Alpha Centauri A, the way it currently orbits the Sun. At our familiar 93 million miles, it would, for at least part of every Centauri B orbital cycle, find itself living inside a system where a second Sun-sized star is swinging through the neighborhood every few decades, occasionally coming close enough to seriously disturb everything that depends on gravitational stability. This is the first thing the thought experiment reveals, and it's bigger than most people expect. The question isn't really what would the sky look like. The question is, would there even be a stable orbit at all? And to answer that, astronomers had to do something unusual. They had to calculate, mathematically, where in this three-star system a planet could survive long-term, and where it absolutely could not. There's a concept in orbital dynamics called stability zone, and it sounds dry until you understand what it's really describing. The line between a planet that keeps a sane, repeating orbit for billions of years, and a planet that gets gradually shredded out of its path by a second star's gravity until it's flung into deep space, dropped into its sun, or simply scattered into chaos. For Alpha Centauri A and B specifically, decades of research, including detailed numerical simulations, run specifically because Centauri is the closest system to us, and therefore the most tempting target for a future probe, have mapped out where stable orbits are even mathematically possible. The rough answer: a planet can orbit Alpha Centauri A safely if it stays within roughly 2 to 3 astronomical units of it. An astronomical unit, for reference, is the Earth-Sun distance, about 93 million miles. So a planet orbiting comfortably within that zone, well inside the gravitational moat that Centauri B's wandering presence carves out, can have an orbit nearly as clean and circular as Earth's is now. This matters enormously for our thought experiment, because it tells us something we didn't expect going in. Earth, dropped into the Alpha Centauri system at the right distance, isn't doomed by definition. There genuinely is a place in that system where a planet's orbit can remain mathematically stable for a very long time. The system isn't automatically a wrecking yard, but stable and comfortable are not the same word. If Earth orbited Alpha Centauri A at the same distance it currently orbits the Sun, 1 astronomical unit, it would sit close to the inner edge of that stable zone, in the region researchers consider survivable, but increasingly perturbed the farther out you push out to 2 astronomical units and beyond, and the gravitational influence of Centauri B starts measurably stretching and tugging the orbit during the years when the 2 stars swing closest to each other. So here is the first real discovery hiding inside this thought experiment, and it's worth sitting with for a moment. The presence of a second star doesn't necessarily destroy a planet's orbit. It reshapes the rules of what a normal orbit even means. An orbit that would be silky smooth and unchanging around a single star becomes, around a binary, something closer to a long, slow breathing motion, expanding and contracting slightly as the second star approaches and retreats over the decades, which raises the next question, the one that actually determines whether anyone could have lived through this version of Earth's history at all. What would the climate do? Our seasons exist because Earth's axis is tilted relative to its orbital plane. And as we travel around a single, steady sun, different hemispheres lean toward or away from that one source of warmth at different points in the year. It's elegant. It's also completely dependent on there being exactly one source of warmth whose distance and angle change in a smooth, repeating pattern, year after year, century after century. Introduce Alpha Centauri b into the equation, and the entire machinery of a year gets more complicated. Not necessarily broken, but far stranger than anything in human experience. Here's the key fact that changes how this thought experiment plays out. Alpha Centauri b, even at its closest approach to Centauri A, never gets remotely close enough to a planet orbiting tightly around A to act like a second sun in any meaningful day-to-day sense. At minimum separation, B sits more than 10 times farther from a planet at 1 astronomical unit than the Moon is from Earth's orbital radius relative to the Sun. Actually, more precisely, B at closest approach is still around 11 times farther from A than Earth is from our Sun. From the surface of our relocated Earth, Centauri B would not appear as a blazing second daytime sun, scorching the planet on alternating schedules. It would appear, even at its brightest and closest, as an extraordinarily brilliant point of light, far outshining every planet and star in our actual night sky, dramatically brighter than Venus ever gets for us. But a point of light nonetheless, not a second disk, providing real daytime heat. This is one of those places where the wait, what? Moment works against the obvious assumption. Most people picture a planet with 2 suns and imagine 2 blazing orbs sharing the daytime sky, doubling the heat, alternating who rises and who sets. The reality for a planet tucked safely in the inner stability zone of Alpha Centauri A is quieter and stranger. 1 true sun, providing essentially all the warmth and light that sustains the biosphere, and 1 extraordinarily luminous companion star that dominates the night sky instead, Ed. Sometimes bright enough to cast faint shadows, always present, slowly changing position over decades, as the 2 stars complete their long orbital waltz. So the seasons themselves, on a basic level, would still come from Centauri A's distance and our planet's axial tilt, much like they do now. But there's a second, slower layer of change stacked on top of the familiar yearly cycle. Something Earth has simply never experienced. An 80-year rhythm driven by the changing distance between the 2 stars, subtly modulating the system's gravitational and radiative environment over a human lifetime. A person born when Centauri B is near its farthest point in that 80-year cycle would live through their entire childhood, adulthood, and old age while the 2 stars gradually swing closer together, watching the companion star slowly brighten in the night sky across decades. A visible, trackable countdown of cosmic time layered directly onto a single human life. Their grandchildren might be the ones to witness closest approach. It would be a calendar far longer than a human lifespan, but for the first time, slow enough and close enough to actually notice within 1. Civilizations on Earth have built entire belief systems, calendars, and cultural identities around the steady, dependable cycle of 1 sun and 1 moon. What happens to a civilization that grows up watching a second star visibly brighten and dim across the arc of human generations? We'll come back to that, because the sky is only the beginning of how different this version of Earth would actually feel. And the next complication isn't really about the second star at all. It's about something far more familiar and far more vulnerable than anyone usually realizes. It's about the moon. Here is something that almost never comes up when people imagine Earth orbiting a different star. The moon isn't guaranteed to come with us. Earth's moon orbits us at an average distance of about 239,000 miles, held in place by a delicate balance between Earth's gravity pulling it inward and its own orbital motion flinging it outward. That balance has held for over 4 billion years because nothing nearby has ever seriously challenged it. The Sun is gravitationally significant to the Earth-Moon system, gently tugging on both, but it's far enough away, and Earth's pull on the Moon is strong enough that the system stays bound. Now add a second sun-mass star, swinging through the system every 80 years, sometimes coming within roughly 10 to 12 times the Earth-Sun distance of the inner planets. Researchers who specifically model moons in binary star systems have found something important: a moon orbiting close to its planet, within roughly half the distance at which the planet's own gravity would start losing the tug-of-war to outside forces, tends to remain stable even when a second star periodically swings through the system. Our actual moon orbits well within that safety margin relative to Earth. This is genuinely good news for our thought experiment. The moon likely survives. It keeps raising tides. It keeps stabilizing Earth's axial tilt, which is one of its most underappreciated jobs. Without something nearby acting as a gyroscopic anchor, a planet's axial tilt can wander chaotically over millions of years. And Mars, which has no large moon, shows exactly this kind of wobble in its geological history. Earth's moon has spared us that fate for billions of years. But likely survives is not survives with zero change. Over the kind of timescale evolution actually operates on not 80 years, but 80 million years, 800 million years. The repeated gravitational nudging from Centauri B's closest approaches would very slowly perturb the fine details of the moon's orbit. Not enough, in most simulated scenarios, to tear it away, but enough, potentially, to very gradually alter the precise rhythm of the tides, the exact angle of axial tilt over deep time, the subtle wobbles that geologists actually read in ancient rock back on the real Earth to reconstruct our planet's climate history. Which means that somewhere in this story, a strange and almost dizzying realization starts to surface. A 4 billion year long evolutionary history, like the one that produced humans on Earth, might not unfold the same way twice, even with the exact same starting planet, simply because the background, gravitational hum of the system is different. Same Earth, same moon, same starting chemistry, different stars next door. Possibly, over deep enough time, a different evolutionary outcome entirely. That's the first time this thought experiment stops being a curiosity about skies and starts becoming a question about us. About whether the life we know, the species we are, depended not just on Earth, but on the precise quiet of the system Earth happened to grow up in. We'll keep pulling on that thread. But first, there's a far more immediate problem. One with much less patience than slow orbital drift over millions of years. It's the problem of light. Alpha Centauri A is often described casually as almost identical to the Sun. And that description is doing real work in making this thought experiment seem easy. If the star is basically the same, shouldn't the planet just work the same way? Almost. Not quite. And the gap between almost and exactly turns out to matter. Alpha Centauri A is slightly more massive than the Sun, slightly larger, and slightly more luminous. Roughly 1.5 times as bright as our Sun in terms of total energy output. That might sound like a small difference, the kind of rounding error you could ignore. It is not. Stellar brightness translates directly into how much energy reaches a planet's surface. And that energy budget is one of the tightest, most sensitive levers controlling whether a world is a frozen wasteland, a temperate garden, or a runaway greenhouse. If Earth orbited Alpha Centauri A at exactly 1 astronomical unit, the same comfortable distance it orbits the Sun now, it would be soaking up roughly 50% more stellar energy than it currently does. That is not a subtle warming. That is the kind of energy increase that, applied to the Earth's actual climate system, would very plausibly push the planet into runaway greenhouse territory. Oceans boiling away into a thick, opaque steam atmosphere, any chance of liquid water vanishing, surface temperatures climbing to levels no terrestrial organism has ever evolved to handle. So the honest answer to, would Earth be fine around its Sun's near twin, is not at the same distance. Earth would need to sit farther out. Researchers calculating habitable zones for Alpha Centauri generally place the comfortable liquid water supporting zone, some whence around 1.2 to 1.3 astronomical units from the star, a bit farther out than Earth currently orbits the Sun, in order to receive roughly the same energy balance Earth enjoys today. And here's where the story gets genuinely elegant, in a way that almost feels designed, even though it's just orbital mechanics, doing what orbital mechanics does. That adjusted distance, comfortably out past 1 astronomical unit, but still safely inside the 2 to 3 astronomical unit boundary, where Centauri B's gravity starts seriously disturbing things, fits. There is room. The habitable zone around Alpha Centauri A and the dynamically stable zone, where a planet's orbit won't be wrecked by the companion star, actually overlap. This is not guaranteed in every binary star system in the galaxy. In many binaries, the habitable zone and the stable zone don't line up at all. Either the second star is close enough that any orbit warm enough to hold liquid water gets torn apart, or the only stable orbits are so far out they're permanently frozen. Alpha Centauri, as it happens, is one of the more forgiving arrangements nature could have built. It's part of why, when astronomers list candidate systems where an Earth-like planet might plausibly exist and survive, Alpha Centauri A keeps appearing near the top. So our relocated Earth, nudged out to roughly 1.2 astronomical units instead of its familiar 1.0, could in principle receive a survivable, Earth-like energy budget from Alpha Centauri A, while still sitting safely inside the zone where Centauri B's gravity merely perturbs the orbit gently instead of destroying it outright. That's the good news, and it deserves to be taken seriously. Because it means this thought experiment isn't a story that ends immediately in disaster. There is a version of this where the planet works. But the planet works, and the civilization that depends on the planet works, are two very different claims. And this is where the story turns from astrophysics into something closer to anthropology. Because a slightly different orbit, a slightly different year length, a slightly brighter neighboring star, and an 80-year gravitational heartbeat in the background don't just change the climate. They change what it would have meant to be human. Move a planet from 1 astronomical unit to roughly 1.2 astronomical units, and you change its orbital period, the literal length of its year, because of a relationship astronomers have understood since Kepler. Orbital period depends on both distance and the mass of the star being orbited. Run the numbers for a planet at 1.2 astronomical units around a star, roughly 1.1 times the Sun's mass, and you get a year a little over 13 months long by our current calendar. Somewhere in the neighborhood of 400 days. depending on the precise final orbital distance chosen for habitability. Not wildly different from what we're used to, but different enough that every calendar, every agricultural cycle, every religious festival tied to the timing of seasons in actual human history would have needed to be built around a different number from the start. This sounds like a footnote. It is not. Human civilization's earliest organized institutions, Babylonian astronomy, Egyptian flood calendars tied to the Nile, the Mayan calendar systems, the foundational mathematics that eventually grew into modern astronomy itself, exist specifically because early humans were trying to predict a repeating solar year accurately enough to know when to plant and when to harvest. Get the year length wrong by even a few days, accumulated over centuries, and an agricultural society's entire food security collapses into seasonal confusion. The earliest civilizations that solved this problem most precisely tended to become the most stable, most powerful, most enduring ones. A 400-day year isn't disastrous, but it's a different problem to solve, a different rhythm to discover, a different set of numbers humanity's earliest astronomer priests would have needed to work out from scratch, watching a slightly brighter sun trace a slightly longer arc across the sky. And underneath all of that, slowly, almost imperceptibly across centuries, that second light in the night sky, Centauri b, would have been doing something the moon and stars never do for us, visibly changing. Across one human lifetime, Centauri b's position relative to Centauri a would shift, brighten, dim, depending on where the 80-year cycle stood. Ancient astronomers on this version of Earth wouldn't just be tracking one sun's path and a moon's phases. They'd be tracking a second, much slower wanderer, bright enough to demand attention, slow enough to defy easy explanation for a very long time, mysterious enough to almost certainly become wrapped in religious significance long before anyone understood orbital mechanics. Every culture on the actual Earth that has ever looked up and seen something irregular in the sky, a comet, an eclipse, a nova, built mythology around it. A second star, visibly brightening and dimming across decades, sitting permanently in the night sky, rather than appearing once and vanishing, would almost certainly have become one of the most central objects in early human religious and astronomical thought. Long before telescopes, before anyone understood gravity, humans on this version of Earth would have been staring at unmistakable evidence that the universe contained more than one sun. Centuries, possibly millennia, before anyone here actually figured that out for real. That's worth pausing on, because it inverts something we normally take for granted about the history of astronomy. On the real Earth, the idea that other stars might be suns like our own, true centers of their own planetary systems, was a genuinely hard-won realization, developed over centuries, resisted for a long time, only really cemented as obvious common knowledge in the last few hundred years. On this version of Earth, with one of the system's two major stars hanging visibly, undeniably in the night sky, slowly changing brightness on a timescale a person could track within their own life, that realization might have arrived astonishingly early. The sky itself would have been quietly teaching the lesson long before the science caught up, which leads to a genuinely strange thought. In some very real sense, the Alpha Centauri version of human civilization might have understood that stars are other suns earlier than we did, not because they were smarter, but because the evidence was simply staring down at them every single night, impossible to ignore. Let's slow down here and actually build the picture, because this is the part of the thought experiment people most want to see, and it deserves to be done carefully rather than dramatically. During the day, the dominant presence in the sky is Alpha Centauri A. And because it's slightly larger and slightly more luminous than our Sun, and because our relocated Earth sits a bit farther out at around 1.2 astronomical units, the apparent size of the star in the sky would actually be very close to the apparent size of our familiar Sun, not dramatically larger, not dramatically smaller. A careful, almost coincidental near match in apparent disk size. Even though the absolute numbers underneath are different, the light would carry a faint difference in temperature, slightly whiter, with a touch less of the soft yellow warmth we associate with our actual Sun, owing to Centauri A's marginally hotter surface. But to most human eyes, on a casual glance, the daytime sky might look almost unsettlingly familiar. The real difference shows up after sunset. Alpha Centauri B, even at its average distance from A across the 80-year cycle, would appear in the night sky as something genuinely unprecedented in human visual experience. A point of light far brighter than any star or planet in our actual sky. Brighter even than Venus at its most brilliant, yet still unmistakably a point rather than a disk. No warmth, no daytime presence, just an extraordinarily intense pinprick of light, sometimes visible even before the sky fully darkens, casting just barely enough light on a clear, dark night to be noticeable, though nowhere near as bright as full moonlight. And depending on where the planet's axis and orbital geometry placed things, there would be stretches of the year and stretches of the 80-year cycle, where Centauri B was visible essentially all night. A second, fainter point of reference threaded permanently through the darkness, never disappearing the way our actual stars rise and set throughout the year, because at certain orbital configurations, it would remain above the horizon continuously for extended periods, depending on latitude. Far out at the edge of the system, Proxima Centauri, small dim, a red dwarf star roughly an eighth the mass of the Sun, orbiting the AB pair at a vast distance, would barely register to the naked eye at all. From a planet tucked in close around Centauri A, it is currently understood to orbit the AB pair at a distance of roughly 8,700 astronomical units, looping around once every several 100,000 years. From up close around A, Proxima would be a faint, unremarkable star, indistinguishable by eye from the thousands of other distant points scattered across the night sky. It is, in the most literal sense, a footnote to this story. Present, gravitationally bound to the system, occasionally relevant to long-term orbital stability calculations, but visually and practically irrelevant to the experience of standing on the planet's surface and looking up. So here is the full picture, assembled piece by piece, rather than imagined all at once. By day, a sky almost eerily similar to our own, lit by a star nearly the twin of our Sun. By night, one true addition to the cosmic backdrop. Not a second sun, but a second presence. A slow-burning beacon, bright enough to notice, mysterious enough to wonder about, permanent enough to build a civilization's entire mythology, and, eventually, its entire science of the heavens around. That alone would have been enough to change everything about how humans understood their place in the universe. But the sky was never really the deepest layer of this thought experiment. The deepest layer is what's happening underneath the ground and to the air and to the water, over the kind of timescale that doesn't care about human calendars at all. Most people who think about Earth orbiting a different star stop at the sky. Fewer people ask what happens to the climate over not 1 year, but 100 million years. The actual timescale on which Earth's biosphere has been quietly, continuously reshaped, again and again, by forces too slow for any human civilization to have ever directly witnessed. This is where the 80-year stellar heartbeat we mentioned earlier stops being a curiosity and starts becoming a serious scientific question. Earth's actual climate history is governed, in large part, by something called the Milankovitch cycles. Slow, repeating changes in the shape of Earth's orbit, the tilt of its axis, and the wobble of that axis, occurring over tens of thousands of years, that subtly shift how much sunlight different parts of the planet receive at different times. These cycles are widely understood to be one of the major drivers behind the timing of ice ages throughout Earth's recent geological past. They are slow, they are gentle, and critically, in our actual solar system, they are also extremely regular and predictable. Because nothing significant disturbs Earth's orbit except the steady, repeating pull of the Sun and the other planets. Introduce Alpha Centauri B's repeating 80-year close approaches into that picture, sustained not for one human lifetime, but for hundreds of millions of years, and you introduce a long-term gravitational disturbance our real Earth has simply never had to deal with. Every 80 years, like clockwork, a second sun-Mars star tugs at the planet's orbit and, more subtly, at the fine details of its axial behavior. Over geological time, those repeating tugs would very plausibly add extra layers of irregularity on top of the Milankovitch-style cycles we're familiar with. Not enough? Based on the same stability research that maps where planets can survive at all. To throw the system into chaos, but enough to mean the climate's long-term rhythm would be a genuinely different rhythm than the one that shaped Earth's actual ice ages, evolutionary bottlenecks, and mass extinctions. This is the point where the thought experiment quietly reveals something uncomfortable. The version of Earth's history that actually produced complex life, then mammals, then primates, then us, wasn't simply a story of the right planet in the right place. It was a story of the right planet in the right place, around the right kind of star, with no nearby gravitational interference, patient enough and strong enough to subtly rewrite the climate's long-term rhythm across hundreds of millions of years. Move that same planet next door to Alpha Centauri, and you don't necessarily kill it. The simulations and stability research broadly suggest the system could remain technically habitable for billions of years. But you very plausibly change its story. Different ice age timing, different extinction pressures, different evolutionary bottlenecks at different moments for different reasons, which means the uncomfortable, fascinating possibility sitting at the center of this entire thought experiment is this. Even with the literal same planet, the literal same starting biosphere, the literal same moon, humanity, as a specific evolved species with this specific history, might never have happened at all. Something might have evolved. Quite possibly something intelligent, eventually, given enough time and a stable enough habitable zone. But not necessarily us. Not necessarily on the same timeline, with the same near misses and survivals that actually produced Homo sapiens. On the real Earth roughly 300,000 years ago. That's not a small detail to discover hiding inside a casual thought experiment about a different sky. That's a question about how contingent, how genuinely lucky our own existence might be on details of our solar system's quiet, single-star simplicity that we almost never think to be grateful for. And we're still only partway through untangling what this system would have actually meant for a civilization that did, against the odds, manage to arise there. Because so far, we've mostly talked about light, orbits, and deep time. We haven't yet talked about something that would have mattered just as much, possibly more, to anyone actually trying to leave the planet and look outward. We haven't talked about what it would mean to live in a star system that is, by an enormous margin, the closest star system to itself. Here's a strange inversion worth sitting with for a moment. On the real Earth, Alpha Centauri is famous specifically because it is the nearest star system to us. Roughly 4.24 light-years away, a distance so vast that even our fastest spacecraft would need tens of thousands of years to cross it using current propulsion technology. Every conversation about interstellar travel, every serious proposal for sending a probe to another star, starts with Alpha Centauri, precisely because it's the only star close enough that the idea isn't pure fantasy. But flip the thought experiment around and put Earth there instead of here, and Alpha Centauri stops being humanity's nearest neighbor. The Sun becomes humanity's nearest neighbor. From a planet orbiting Alpha Centauri A, our actual Sun would appear as a modestly bright star in the night sky, still relatively prominent compared to the broader backdrop of more distant stars, since 4.24 light-years is genuinely close on a galactic scale. But nothing like the blinding daytime presence we're used to. It would be a notable point of light, almost certainly one of the brighter stars visible to relocated humanity's night sky, but indistinguishable in raw appearance from any other ordinary star, unless you already knew exactly where to look and what you were looking for, which means an entire civilization evolving on this relocated Earth might have spent its entire history quietly mistaking our Sun for nothing more than background scenery, never realizing that the unremarkable yellow dot in their night sky was the literal sibling system to their own, the closest other star system in the galaxy, simply because nothing about its appearance from that distance would have screamed special. That single realization captures something important about the entire thought experiment, something that becomes one of its quietest, most powerful threads. How much of what makes a star or a system feel important is really just about distance, and how much of what we currently believe about our own Sun's importance might simply be the accident of being the one we happen to orbit. There is something almost humbling buried inside that. Every culture on the real Earth has, at some point in its history, built mythology, religion, science, and identity around the Sun specifically because it is overwhelming, undeniable, inescapable, the single largest, brightest, most dominant object in the sky, day after day, for the entirety of human existence. That dominance feels, intuitively, like it must mean something, like the Sun must be special. But swap the star, and the same psychological dominance would simply transfer to whichever star happened to be close enough to blaze overhead. The feeling of cosmic significance isn't really coming from the star itself. It's coming from proximity, from the simple mechanical fact of being the nearest the thing large enough to dominate the sky. It's a small thought almost philosophical rather than scientific. But it's exactly the kind of perspective shift this entire exercise keeps circling back toward, again and again, every time we look closely enough at one more piece of the picture, move the position, and the meaning moves with it. The universe doesn't assign significance. Distance does. And that thought sets up the next major question this documentary needs to answer. Because so far we've mostly been looking down at orbits, at climate, at the slow churn of geological time. It's time to look up and ask what this system would have actually meant for any civilization on this relocated Earth that eventually developed telescopes, spacecraft, and a serious scientific ambition to understand exactly what kind of strange three-star neighborhood it had been born into. Because understanding Alpha Centauri from the inside, rather than from 4.24 light-years away, the way we currently do, would have answered some of humanity's oldest astronomical questions almost immediately. And it would have raised entirely new ones nobody on the real Earth has ever had the chance to ask. On the real Earth, studying Alpha Centauri means studying it from outside, pointing telescopes across 4+ light-years of empty space, measuring tiny wobbles in starlight, inferring the existence and orbits of the system's stars through careful, patient, indirect mathematics. It took astronomers centuries of refinement just to confirm that what looked like one star was actually two, and longer still to map their orbit with any real precision. Proxima Centauri wasn't even confirmed as part of the system until the early 20th century, and its exact gravitational relationship to the other two stars remained a genuinely open scientific question for decades after that. Some astronomers weren't entirely certain Proxima was gravitationally bound to the pair at all, until relatively recent, more precise distance and motion measurements settled the matter. A civilization living inside the system wouldn't have that problem. They would have something almost absurdly valuable by comparison: a front-row seat. Centauri B's orbit around Centauri A, instead of being a tiny, painstakingly measured wobble in distant starlight, would simply be observable directly, with the naked eye, across a single human lifetime. Track its position carefully for 80 years, and you'd watch the entire orbit complete from start to finish. No inference required. No centuries of refinement needed to confirm what the two lights in the sky were actually doing. The orbital mechanics of a binary star system, one of the genuinely difficult problems in the history of real astronomy, requiring Newton's gravitational framework and centuries of careful observation to fully crack, would have been sitting there, visible, demonstrating itself, to anyone patient enough to watch and record. This raises a fascinating possibility about the entire trajectory of scientific history on this version of Earth. Gravity itself, the force governing planetary motion, the thing Isaac Newton spent years working out mathematically using nothing but the moon, the planets, and falling apples, might have revealed its secrets faster and more obviously to astronomers who had two visibly orbiting stars sitting in their sky as a built-in physics demonstration. The two-body problem, the foundational puzzle of how two massive objects orbit a shared center of gravity, wouldn't have needed to be reconstructed from subtle indirect evidence. It would have been staring down at them every clear night, slowly tracing its own answer across the decades. It's tempting to imagine that civilization developing physics and astronomy faster than ours did. Tempting, but probably too simple. Faster insight into orbital mechanics doesn't automatically mean faster civilization-wide scientific development across every field. Plenty of other historical, cultural, and technological factors shape how quickly any society builds a scientific tradition. But it's a genuinely interesting asymmetry worth noting. The most important astronomical puzzle our real-world astronomers had to solve through centuries of patient indirect observation might have been for a civilization actually living inside Alpha Centauri. Simply part of growing up and looking at the sky. There's a deeper version of this same idea, too. Once that civilization built telescopes of their own, they wouldn't just be looking outward at distant galaxies the way we do. They'd have a genuinely unusual local laboratory sitting right next door. Proxima Centauri, the small red dwarf orbiting far out at the edge of their own system, would have been one of the closest objects of its kind to study in detail, long before they ever needed interstellar travel to examine a star fundamentally different from their own up close. Red dwarfs are, by far, the most common type of star in the entire galaxy. Roughly 3 out of every 4 stars are some variety of red dwarf. And yet on the real Earth, the nearest one to us happens to be Proxima Centauri itself, studied today only through painstaking observation across more than 4 light years. A civilization growing up inside the Centauri system would have had a genuine red dwarf as a literal next-door neighbor within their own home system, decades or centuries before they had any hope of reaching another star entirely. That detail matters more than it first appears, because it touches directly on one of the biggest open questions in real astronomy today. How common is life likely to be around red dwarf stars, which make up the overwhelming majority of stars in the galaxy? Having an actual nearby example to study, even from within the same broader system, rather than needing interstellar travel, would have given this hypothetical civilization a research advantage that real human astronomers, separated from every red dwarf by years or decades of light travel time, simply don't have. Long before any civilization on this relocated Earth built a telescope, they would have already been collecting evidence about their strange system, not by looking up, but by watching the ocean. On the real Earth, tides come almost entirely from the moon, with the sun contributing a smaller but still measurable pull of its own. The two combine in a predictable rhythm, roughly twice monthly, spring tides, when the sun and moon align and their pulls reinforce each other, and gentler, neap tides when they partially cancel out. Coastal civilizations noticed this rhythm early. Tide tables, in one form or another, are among the oldest pieces of applied astronomy humans have ever produced, because getting them wrong meant losing boats, nets, and sometimes lives. A coastal civilization on this relocated Earth would have inherited the same basic lunar saucer tidal rhythm. The moon's gravity dominating Centauri A's gravity, contributing a smaller seasonal pull, much like our actual sun does. But layered on top of that familiar rhythm would have been something genuinely new, an extremely slow, almost imperceptible tidal nudge from Centauri B, strongest during the years when the two stars swing closest together in their 80-year cycle, and essentially undetectable the rest of the time. No single fisherman, no single generation of coastal astronomer priests would likely have noticed this directly. The effect is far too small, drowned out almost completely by the moon's far stronger and far more immediate pull. But across centuries of carefully kept written tide records, The kind of meticulous, generations-long data collection that real human civilizations like the tide watchers of the ancient Mediterranean and the rice and fish cultures of coastal Asia were already capable of producing. A sufficiently patient society might eventually have noticed a strange, slow distortion creeping into their tide tables every 80 years or so. A small mystery hiding in the numbers long before anyone understood why. That's worth pausing on, because it's a quiet example of something this entire thought experiment keeps demonstrating again and again. The presence of a second star wouldn't necessarily announce itself through anything dramatic or catastrophic. Much of the time, its influence would be subtle, almost hidden. The kind of thing that only reveals itself to a civilization patient enough, organized enough, and curious enough to keep careful records across many human lifetimes. Exactly the kind of slow-building scientific puzzle that, once finally solved, tends to produce some of the most satisfying discoveries in the entire history of a civilization's science. It's also a useful reminder of something true about real Earth's own history. Many of humanity's most important astronomical discoveries, the length of the year, the precession of the equinoxes, the existence of planets too faint and slow-moving to notice in a single lifetime, came not from a single brilliant insight, but from exactly this kind of patient, multi-generational record-keeping. The relocated Earth's astronomers, watching their tides and their second star's 80-year heartbeat, would have been walking the same long, patient road toward understanding their universe that real human astronomers have always walked, just with one more thread in the data, waiting to be noticed. Speaking of Proxima Centauri, it's worth pausing on this star specifically, because in the actual, real Alpha Centauri system, it carries a detail that becomes strangely relevant to our thought experiment, almost like an uninvited subplot. Proxima Centauri is currently known, through real observational data gathered over the past several years, to host at least one planet orbiting within its own habitable zone. A world astronomers have named Proxima Centauri b, discovered through painstaking measurements of the tiny gravitational wobble it induces in its star. It's a planet at least slightly more massive than Earth, orbiting close enough to its dim red star to receive roughly Earth-like levels of energy. Despite Proxima itself being a small, cool, dim star compared to the Sun, red dwarf stars like Proxima are infamous in current astronomical research for a particular hazard. They tend to be far more magnetically active and prone to powerful flares than calmer, Sun-like stars such as our actual Sun or Alpha Centauri A. A planet close enough to a red dwarf to stay warm is also, often, close enough to be regularly blasted by intense stellar flares and radiation, a real and ongoing concern in the scientific debate over whether planets like Proxima b could plausibly support life as we understand it. Here's where it becomes relevant to our thought experiment. In the actual configuration of the real Alpha Centauri system, Proxima Centauri b would be one of our nearest potentially habitable zone neighbors in the literal sense, and a civilization growing up around Alpha Centauri A, looking out at their own system, would eventually find themselves staring at a planet that might be just as fascinating, just as debated, just as central to their own version of the search for life elsewhere as any distant exoplanet is to us, except theirs would be close enough, in relative interstellar terms, to actually consider visiting. A journey of roughly 8,700 astronomical units within their home system. Immense by any everyday measure, but nothing close to the multi-light-year gulf that separates real humanity from any other star system at all. In other words, this relocated civilization might have had its own miniature version of humanity's search for alien life sitting conveniently inside its own backyard. Close enough to dream about visiting, with technology only modestly more advanced than what humanity has already built. Rather than needing the kind of civilization-spanning interstellar leap our real exploration of other star systems currently requires. That's a genuinely strange, genuinely wonderful asymmetry buried inside this thought experiment. We are right now looking outward at Alpha Centauri and dreaming about what it would take to reach it. A civilization born inside Alpha Centauri might have spent its own history looking at Proxima, dreaming about what it would take to reach that, and finding the gap, relatively speaking, dramatically smaller than the one separating real humanity from any star at all. This thread deserves to be followed a little further because it touches one of the most fundamental aspects of how a civilization's entire relationship with space exploration might unfold differently, depending on its cosmic address. On the real Earth, the gulf between us and the nearest other star system, 4.24 light-years, roughly 25 trillion miles, is so enormous that even our most ambitious current interstellar mission concepts, the kind involving a lightweight probes, accelerated by powerful ground-based lasers toward a meaningful fraction of the speed of light, still imagine multi-decade, one-way travel times at best for an unmanned probe weighing only a few grams, sending actual humans to another star system. With current or near-future technology, remains so far beyond practical engineering reach that serious mission planners generally treat it as a multi-generational, centuries-away ambition, rather than something on any foreseeable roadmap. Now consider a civilization that grew up around Alpha Centauri A, with Proxima Centauri sitting at a distance of roughly 8,700 astronomical units, vastly farther than any planet in their own home system, requiring serious advances in propulsion to reach in any reasonable time frame, but representing a single coherent system-spanning journey rather than a leap to an entirely separate star. Their first truly ambitious deep space mission wouldn't need to cross another star's worth of empty void. It would need to cross their own system's outer reaches. A hard problem, certainly, requiring real advances in propulsion and life support, but a fundamentally different category of hard problem than ours, their actual interstellar leap. Reaching the Sun, the nearest other star system, the one we currently call home, would still face the same brutal physics we face today. 4.24 light-years is 4.24 light-years, regardless of which side of the journey you start from. Nothing about being born around Alpha Centauri makes the laws of physics gentler. The speed of light remains an absolute ceiling. The energy required to accelerate any meaningful payload to a significant fraction of that speed remains staggering by any civilization standards, ours or theirs. But here's the genuinely interesting twist. A civilization that had already, out of necessity, solved the considerably easier problem of reaching Proxima Centauri within their own system. Building probes, then eventually crewed missions, capable of multi-decade or multi-century journeys across thousands of astronomical units, would have already developed a meaningful fraction of the propulsion, life support, and long-duration mission engineering that any realistic interstellar mission to our Sun would also require. Their path to genuine interstellar travel might look less like a single, impossible leap and more like a series of increasingly difficult system-spanning missions, each one slightly closer in spirit to what true interstellar travel demands. In a very real sense, that civilization's home system might have functioned as a built-in training ground for interstellar ambition, something the real solar system, with its overwhelmingly dominant single sun and comparatively modest planetary distances, simply doesn't offer to real human engineers in quite the same way. This is exactly the kind of layer the strongest documentaries are built around. Not just answering the surface question of what the sky would look like, but discovering, almost by accident, that the deeper structure of the system would have reshaped that civilization's entire relationship with ambition, distance, and exploration, possibly accelerating certain kinds of progress while still leaving the truly hard problem, crossing 4.24 real light years to reach us, exactly as difficult as it remains for humanity today. There's one more piece of the puzzle that deserves serious attention before we widen the lens any further, because it's the kind of detail that rarely makes it into casual versions of this thought experiment, and it directly determines whether a technically stable orbit actually translates into a world capable of sustaining a 4 billion-year biosphere. Stars are not static, gentle furnaces, quietly radiating the same fixed amount of energy forever. They have weather, in a sense. Magnetic activity, flares, a constant outward stream of charged particles called stellar wind. Our actual Sun is, by the standards of sun-like stars, a relatively calm, well-behaved star at this stage in its life, though it still produces solar flares and occasional coronal mass ejections, energetic enough to disrupt satellites and power grids on the real Earth. Alpha Centauri A and B are both, broadly speaking, similarly calm, mature, sun-like stars, part of why they're considered promising candidates in the first place. Neither is a young, hyperactive star prone to the kind of violent, frequent flaring that plagues many red dwarfs, including, notably, Proxima Centauri itself. This is actually one of the more reassuring details buried in the real astrophysical data about this system. If you had to pick which of the 3 Centauri stars to orbit closely as a long-term home for a biosphere, Centauri A is, by a wide margin, the friendliest option on offer. Calmer magnetic behavior, more stable long-term energy output, none of the violent radiation environment that makes planets around red dwarfs like Proxima such a genuinely contested case in the ongoing scientific debate over habitability. But calmer than a red dwarf doesn't mean identical to the Sun in every respect. And this is where the long-term habitability bill quietly comes due. Alpha Centauri A, being slightly more massive and more luminous than the Sun, also burns through its nuclear fuel somewhat faster, which means its total stable lifetime on the main sequence, the long, steady, fusion-powered phase of a star's life, during which a stable habitable zone can persist for billions of years, is shorter than the Sun's by a meaningful margin. A star roughly 1.1 times the Sun's mass is expected to remain in this stable phase for something on the order of 9 to 10 billion years, somewhat less than the roughly 10 billion year total main sequence lifespan astronomers calculate for our own Sun. That's still an enormous amount of time by any human standard. More than enough for the entire 4 billion-year history of life on the real Earth to have played out, with billions of years left over. It's not a looming catastrophe for our thought experiment, but it does mean that this relocated Earth, even in its best case, most stable configuration, would have been living on a very slightly shorter cosmic clock than the one our actual planet enjoys. A detail invisible to any single human civilization, but real on the scale that actually determines how long a planet remains capable of supporting complex life before its star's slow evolution eventually pushes the habitable zone outward and leaves the planet behind. So, where does this leave us? Halfway through untangling what might be one of the most quietly profound thought experiments in casual astronomy. A question that sounds, on the surface, like simple cosmic trivia. But that turns out to touch orbital mechanics, deep-time climate history, the evolution of intelligent life, the entire trajectory of a civilization's scientific development, and the true difficulty of interstellar travel. All at once. Here is what we've actually established so far, carefully, piece by piece, rather than assumed. A planet identical to Earth, placed in a carefully chosen orbit around Alpha Centauri A, roughly 1.2 astronomical units out, comfortably inside the zone where Centauri B's gravity merely perturbs rather than destroys, could plausibly remain in a stable, life-supporting orbit for billions of years. That alone is a genuinely significant finding, because it means this isn't simply a story about an impossible, doomed world. There is a real, scientifically grounded version of this scenario where the planet survives. But survival and familiarity are different things. The year would be longer. The climate's deep-time rhythm would carry an extra, unfamiliar layer of gravitational interference from Centauri B's repeating 80-year approach, subtly reshaping the planet's ice age and extinction history across geological time, in ways that might never have produced the specific evolutionary path that led to modern humans on the real Earth. The Moon would likely survive too, continuing to stabilize the planet's axial tilt, though its orbit would carry the same subtle long-term perturbations as everything else in the system, and the sky, the most immediate, daily experience of living there, would have been almost eerily familiar by day and genuinely unprecedented by night. A brilliant, slow-changing companion star, visible across an entire human lifetime, almost certainly becoming one of the most central objects in that civilization's entire religious, mythological, and eventually scientific history, possibly teaching them centuries earlier than it took us to learn that the points of light scattered across the night sky are themselves other suns. We've also discovered something quietly humbling. The same gravitational dominance that makes our actual sun feel cosmically significant to every human culture that has ever existed is, in the end, just a function of distance and proximity, nothing more. And that significance would transfer effortlessly to whichever star happened to be close enough to blaze overhead on whichever planet happened to be orbiting it. And we've discovered, perhaps most strikingly of all, that this relocated civilization's entire relationship with space exploration might have unfolded in a completely different shape than ours. A built-in, system-spanning training ground in the form of Proxima Centauri sitting at the edge of their own system, close enough to dream about reaching with foreseeable technology, even while the truly impossible leap, the 4.24 light-year journey to reach the very system we currently call home, would have remained every bit as forbidding to them as it remains to us today. None of this is science fiction. Every distance, every mass ratio, every orbital stability boundary referenced here comes from real, published research into the actual Alpha Centauri system. Research conducted specifically because this is the one star system close enough that scientists have genuine reason to ask whether a planet could survive there and whether one day humanity might actually go and see for ourselves. But we've only covered half of the real question. We've established that the planet could plausibly survive, that the sky would be strange but not impossible, that a civilization could very plausibly rise there. What we haven't yet asked is the deeper question this entire thought experiment has been quietly building toward from the very beginning. The question that turns this from an exercise in orbital mechanics into something closer to a meditation on the entire nature of cosmic luck. What would it have meant for that civilization to eventually look out and realize the truth about their own existence? That they were living inside one of the rarer, more delicately balanced configurations the universe is capable of producing? What would it have meant for them to turn their telescopes toward our quiet, single, unremarkable sun and wonder what it might be like to live somewhere so much simpler than home? And what does any of this, finally, tell us about the actual Earth we're standing on right now? About the silence of our own sky, and whether that silence was ever really an accident at all. There's a particular kind of vertigo that comes from flipping a thought experiment around to look at itself from the other side. And this is the moment in the story where that vertigo really sets in. Imagine, for a moment, that this relocated civilization, born under two suns, raised on tide tables that quietly hid an 80-year mystery, taught from childhood that the night sky contained at least one other star bright enough to matter, eventually built telescopes powerful enough to study our actual sun in real detail. Not as a curiosity, as a serious object of scientific interest, the same way we currently study Alpha Centauri. What would they see? They would see a star that is, in almost every measurable way, less remarkable than their own. Slightly smaller, slightly dimmer, burning slightly cooler. A single star, with no visible companion locked in any nearby orbit, sitting quietly by itself in space, the way the overwhelming majority of stars in their observable sky also do. Nothing about it would scream for attention. Nothing about it would look, to a curious young astronomer on that world, like the obvious candidate for hosting a second cradle of life. And that is exactly the strange, valuable inversion this whole exercise has been quietly building toward. From where we actually stand, Alpha Centauri looks special, because it's close, because it's bright, because it's the most famous star system in the night sky outside our own. From a planet inside Alpha Centauri, our sun would look almost defiantly ordinary, a calm, single, modest star. The kind of system most astronomers studying exoplanets today would, if anything, consider an easier place to imagine life arising, precisely because it lacks the orbital complications a binary star system imposes. Here's the detail worth sitting with. They would, in a sense, be right to think that. A single star system really is, by most current models of planetary stability, a simpler, gentler cradle for a long-lived biosphere than even the most favorably arranged binary. Real human astronomers searching nearby systems for habitable planets factor exactly this consideration into their priority lists. Single, sun-like stars without close stellar companions are treated. in current research as inherently friendlier targets, all else being equal, than binaries where stability has to be carefully checked, star by star, orbit by orbit, before a planet's habitability can even be seriously discussed. Which means that if this relocated civilization ever turned a sufficiently advanced instrument toward our actual solar system and began modeling it the way real human scientists model Alpha Centauri, they might have arrived at a quiet, humbling realization of their own, that the system we call home, single star, wide, stable, habitable zone, no companion star, dragging an 80-year gravitational tide through the outer solar system every human lifetime, might actually be the gentler, more fortunate one, not the other way around. It's a small thing, almost a throwaway detail in the grand sweep of everything this thought experiment has uncovered. But it's also exactly the kind of perspective shift the best space documentaries are built to deliver. The moment where you realize that the question, which place would be the better cradle for life, doesn't have a single fixed answer. It depends entirely on which side of the telescope you're standing on. From here, their system looks rare and dramatic. From there, our system would look rare and enviable. Both views would be capturing something true. Step back from the thought experiment for a moment, and there's a genuinely important scientific point hiding underneath all of this. One that connects directly to a question real astronomers are actively working on right now. Using real telescopes, looking at real exoplanets discovered around real stars scattered across the galaxy. For most of the history of exoplanet science, the search for potentially habitable worlds focused overwhelmingly on single-star systems, partly because they're simpler to model and partly because early intuition suggested binary and multiple star systems would almost certainly be too gravitationally chaotic to host anything stable enough to matter. A planet trying to orbit two stars at once, the thinking went, would either get flung out of the system entirely, crash into one of the stars, or end up on such a wildly unstable path that no biosphere could ever take root and persist across the hundreds of millions of years. Evolution actually requires. But as researchers have built better and better simulations, many of them, notably, run specifically using the Alpha Centauri system as the test case, precisely because it's the nearest and most thoroughly characterized binary we have. That early intuition has turned out to be only partly true. It turns out there genuinely are stable zones inside many binary star systems, where a planet's orbit can remain calm and life-friendly for billions of years, provided the geometry works out, the right separation between the stars, the right planetary distance, the right alignment of orbits. Alpha Centauri A and B, as this entire thought experiment has shown step by step, happen to fall into a genuinely favorable arrangement. One of the better real-world examples of a binary system where the dynamically stable zone and the life-friendly habitable zone actually overlap. This matters far beyond just Alpha Centauri because of a simple, striking fact about the broader galaxy. A large fraction of all star systems are not single stars at all. Binary and multiple star systems are extremely common throughout the galaxy. By some estimates, roughly half or more of all star systems contain two or more gravitationally bound stars rather than just one. If it turned out that stable, life-supporting planets were essentially impossible around binary stars that would have quietly written off a huge fraction of all the real estate the galaxy actually offers for potential life. But the Alpha Centauri research suggests the opposite. Under the right conditions, multi-star systems can still host worlds capable of remaining stable and warm enough for life to take hold, for the kind of staggering timescales that complex biospheres actually require. In other words, this thought experiment that began as a playful "what if we lived next door" question turns out to double as a genuine, scientifically meaningful test case for one of the biggest open questions in the modern search for life beyond Earth. Are binary star systems viable cradles for biospheres, or are they mostly dead ends? Alpha Centauri, precisely because it's close enough to study in extraordinary detail, has become one of the most important real-world laboratories for answering that question. And the answer, cautiously, provisionally, based on everything we've walked through so far, leans toward yes, under the right circumstances, they really can work. That's a genuinely exciting thing to realize halfway through a thought experiment that started with something as simple as asking what the sky would look like with two suns in it. So far, this entire journey has quietly assumed a specific choice: that our relocated Earth orbits Alpha Centauri A, the larger, brighter, more sun-like of the two main stars. That choice wasn't arbitrary. It's the version of this thought experiment that real astrophysical research actually favors, and for good reason. But the question deserves a fair hearing from the other direction too, because the alternative, a planet orbiting Alpha Centauri B instead, turns out to be its own small, fascinating detour, and it sharpens, by contrast, exactly why Centauri A was the better choice all along. Alpha Centauri B is the smaller, dimmer, slightly cooler of the two main stars, about 0.9 times the mass of the Sun, with roughly half its total luminosity. A planet orbiting close enough to Centauri B to receive Earth-like levels of warmth would need to sit noticeably closer than 1 astronomical unit, somewhere in the range of 0.7 to 0.8 astronomical units, comfortably inside the distance Mercury and Venus occupy in our actual solar system. That detail alone introduces a new complication: the dynamically stable zone around Centauri B, the region where Centauri A's gravity doesn't dangerously disturb a planet's orbit, turns out to be slightly tighter than the equivalent zone around Centauri A, simply because B is the lighter of the two stars, and therefore more easily pushed around by its heavier companion's gravitational pull. The math still works out favorably. Researchers modeling this exact scenario have found that the habitable zone around Centauri B and its dynamically stable zone do still overlap, much as they do around Centauri A. But the margin for error is narrower, and the planet would sit closer to the inner edge of what's considered safely stable. There's a second, more immediately practical difference too. A planet orbiting that much closer to its star, in order to stay warm enough around a dimmer sun, would also experience a meaningfully faster orbital period. A shorter year, not a longer one. The opposite effect from what happens around the brighter, more luminous Centauri A. Kepler's relationship between orbital distance and period cuts both ways. Move closer to a star, and the year shrinks. Move farther out, as we calculated earlier for Centauri A, and the year stretches. A planet snug in the habitable zone of Centauri B might complete an orbit in something closer to 290 days, a meaningfully shorter year than Earth's current calendar, demanding its own distinct solution to the ancient problem of tracking seasons and harvests. And the night sky, in this version of the thought experiment, would flip its emphasis entirely. From a planet-hugging Centauri B, Centauri A, the larger, brighter star, would now be the dramatic, ever-present nighttime companion, swinging through its 80-year orbit just as before, but now playing the role of the brilliant outsider, rather than the warming daytime star. The basic shape of the story stays the same. The roles simply trade places, depending on which star you call home. So why does the real research and this documentary ultimately favor Centauri A as the more interesting and more favorable version of the scenario? Partly because its larger stable zone offers a bit more margin for error in an inherently uncertain calculation. Partly because Centauri A's closer match to our actual sun's mass, temperature, and total luminosity makes the resulting planet's experience, its colors, its apparent solar disk size, its overall energy balance, feel meaningfully closer to the Earth we actually know. But the Centauri B version isn't a dead end. It's a genuine, scientifically plausible alternative. Just one with a slightly tighter margin and a shorter year, rather than a longer one. Two different versions of the same basic story, both ultimately constrained by the same underlying binary star geometry. Both still ultimately survivable, given the right careful placement. Up to this point, the entire thought experiment has treated the relocated planet as a finished, pre-existing fact. Earth simply teleported into a new orbit, biosphere and all, and then asking how that biosphere would fare. But there's a related, equally fascinating version of this question worth addressing before we move toward the bigger philosophical payoff. Could a real human civilization, rather than imagining a magically relocated Earth, actually attempt to engineer a habitable world inside the real Alpha Centauri system, using a planet that's already there, or one transported by far more modest means than teleporting an entire biosphere across the galaxy? This question connects directly to real, ongoing scientific and engineering discussions about terraforming, the deliberate, large-scale modification of a planet's atmosphere, temperature, and surface chemistry to make it suitable for life. Most current serious terraforming discussion focuses on Mars, simply because it's close, well-studied, and already sits at least loosely within our own sun's habitable zone. But the same basic engineering questions apply to any candidate world, including a hypothetical rocky planet discovered someday within Alpha Centauri's dynamically stable zone. If such a planet were eventually found, rocky, roughly Earth-sized, sitting in that same carefully calculated 1.2 astronomical unit equivalent zone around Centauri A, the fundamental terraforming challenges would mirror the ones already under serious discussion for Mars and other candidate worlds. Building or thickening an atmosphere capable of trapping enough heat and shielding enough radiation, introducing water in stable, sustainable quantities, and eventually establishing the kind of biological feedback loops, plants, and microorganisms working in tandem with the physical environment that could make a world genuinely self-sustaining over long timescales, rather than dependent on permanent artificial life support. The added complication unique to this system would be exactly the one we've spent this entire documentary mapping out. Any successful terraforming engineering would need to specifically account for Centauri B's repeating 80-year gravitational nudges, baking long-term orbital stability, monitoring, and possibly periodic course correction into the planet's basic infrastructure. in a way Martian terraforming planning never has to consider, simply because Mars, like Earth, orbits a single star undisturbed. This is, admittedly, the most speculative chapter in this entire journey. Real terraforming technology, even for the comparatively simpler case of Mars, remains decades or centuries away from serious implementation, let alone applied to a planet 4 light-years distant. But it's worth including briefly because it completes an important piece of the larger picture, even if no naturally Earth-like planet is ever confirmed around Alpha Centauri A. The dynamical and habitability research already completed for this system means we already know, in broad outline, what an engineered solution would need to account for, should some future civilization, ours or, in the spirit of this thought experiment, some other one entirely, ever attempt to build a world there, rather than simply imagining one. There's a deeper question lurking underneath everything we've covered so far. One that connects this entire thought experiment to one of the most famous open puzzles in all of astronomy, the Fermi paradox, the unsettling observation that, given the sheer number of stars and potentially habitable planets in our galaxy, we might reasonably expect to have detected some sign of other intelligent civilizations by now. And yet, as far as our current instruments can tell, the universe appears completely silent. Alpha Centauri occupies an unusually important position in that conversation, precisely because of its proximity. If any nearby star system were going to reveal a hint of intelligent life through reasonably achievable means, radio signals, atmospheric biosignatures, detectable by next-generation telescopes, an unusual pattern of light that didn't match any known natural process. Alpha Centauri, being the closest star system to us, would be one of the very first and easiest places to look. In some sense, it functions as the nearest possible answer key for the entire question of how rare or common life and intelligence actually are in the universe. So far, the answer key has come back blank. No confirmed planet, no detected biosignature, no anomalous signal. This relocated thought experiment lets us ask the question from a genuinely useful new angle. If a stable, life-supporting planet really could exist around Alpha Centauri A, and the orbital mechanics research we've walked through across this entire documentary suggests it plausibly could, then the absence of any confirmed planet there at all becomes a small, quiet data point in the broader Fermi paradox conversation. It's not proof of anything. A planet could exist there right now, simply too small, too faint, or too well hidden in its star's glare for our current instruments to have confirmed it yet. But every year that passes without a confirmed Earth-like world at the one nearby system, where we have both the strongest motivation and the most refined instruments to look quietly, adds a small amount of weight to the broader, more troubling question of just how common or how rare habitable, life-bearing worlds might actually turn out to be, even in the most favorable nearby cases. This is also where the thought experiment's deepest, most existential thread finally surfaces fully. We've spent this entire journey establishing that a version of Earth, plausibly, scientifically, could survive and even flourish inside Alpha Centauri's gravitational arrangement. We have not established that it actually does. The difference between could and does is, in the end, the entire unanswered mystery sitting at the heart of the search for life beyond our own world. And Alpha Centauri, simply by being close enough to actually test that difference against real observational data has become one of humanity's most important proving grounds for finding out. Let's return for a moment to the civilization itself. Not the orbital mechanics, not the search for planets, but the people who might have actually lived under this strange, doubled sky, because this thread deserves more careful attention than a single passing mention earlier in the journey. Every religious and mythological tradition on the real Earth has, in some form, grappled with the motion of the heavens, the sun's daily and yearly cycle, the moon's monthly phases, the unpredictable, terrifying appearance of comets and eclipses, often interpreted as omens precisely because they violated the otherwise reliable, repeating rhythm of everything else in the sky. Ancient cultures built entire cosmologies, calendars, festivals, and origin myths around trying to make sense of a sky that, for the most part, behaved with comforting, predictable regularity, punctuated occasionally by genuinely startling exceptions. A civilization growing up beneath Alpha Centauri A and B would have inherited a sky with one additional permanent irregularity baked directly into its normal, expected behavior, not a rare omen appearing once in a generation, but a constant, ever-present second light, slowly, visibly changing position and brightness across the span of a single human life. That's a fundamentally different relationship with celestial irregularity than anything in real human religious history. Comets and eclipses on the real Earth are terrifying specifically because they're rare and unpredictable departures from an otherwise reliable order. Centauri B, in this scenario, would be the opposite. A fully expected, fully predictable irregularity, present every single night of every single year, its slow brightening and dimming eventually understood, charted, anticipated across generations once enough careful record-keeping had accumulated. It's tempting to imagine that this civilization's mythology might have centered less on fear of the unpredictable and more on a kind of patient, generational storytelling. Myths and religious traditions built specifically around long cycles, around the idea that some celestial events take an entire human lifetime, or several, to complete, and that wisdom and understanding passed down across generations, specifically because no single person could ever watch the entire 80-year story unfold from beginning to end on their own. Coming-of-age rituals tied not to the yearly calendar alone, but to where a person's birth fell within Centauri B's long orbital cycle. A child born during closest approach, when the companion star burns brightest in the night sky, might have carried a different cultural significance than one born during the faint, distant years of the cycle's far side. None of this can be stated as established fact, of course. This moves from astrophysics into genuine speculation about cultural and religious development, and honest speculation should always be labeled as exactly that. But it's a worthwhile speculative exercise, precisely because it illustrates something real and important. The physical shape of a planet's sky doesn't just shape its astronomy. Historically, on the real Earth, it has shaped religion, philosophy, art, agriculture, and the deepest cultural stories a civilization tells about its own place in the universe. A genuinely different sky, even one built from entirely real, scientifically grounded orbital mechanics, would very plausibly have produced a genuinely different civilization, carrying genuinely different stories, even if the underlying species and starting biology were identical to our own. Step away from mythology and deep time for a moment and consider something smaller and more immediate. What an ordinary day, an ordinary season, an ordinary harvest would have actually felt like for someone living an entirely unremarkable life on this relocated Earth. Morning would arrive much as it does here. Centauri climbing over the horizon, warming the air, casting the kind of long, familiar shadows any human being on the real Earth would recognize without hesitation. The slightly cooler, whiter quality of its light, compared to our actual sun, would likely fade into the background of ordinary perception. Within a generation or two, the way any sensory baseline eventually becomes invisible simply through familiarity. Crops would still need to track the angle and intensity of that one true daylight source, and a longer, roughly 400-day year would mean longer growing seasons stretched across a correspondingly longer calendar. Agricultural societies would have needed to work out, through the same patient trial and error that shaped real human farming history, exactly how that extended year redistributed itself across planting, growth, and harvest. The difference would show up most vividly at dusk. As Centauri A dipped below the horizon and the sky darkened, Centauri B would already be there, waiting, sometimes a brilliant point hanging conspicuously in the twilight, even before true darkness fell. Depending on the specific point in its 80-year cycle and the planet's own axial tilt at that particular point in its longer year, there would be long stretches, months, depending on latitude and season, when Centauri B never fully set at all, remaining visible through the entire night as a permanent, unblinking companion to the stars. Farmers working late, travelers navigating after dark, anyone simply stepping outside on an ordinary evening would have done so under a sky that was never quite as fully, completely dark as the real Earth's night sky can be on a clear, moonless evening. A faint, persistent extra source of light. Not nearly bright enough to read by, but enough to subtly soften the deepest darkness in every single season for the entirety of human history there. This detail connects to something genuinely interesting about real biology too. A great deal of life on the actual Earth, from nocturnal animals to certain plants whose flowering cycles depend on precise darkness cues, to the deep, evolutionarily ancient human relationship with truly dark nights, has evolved specifically around the contrast between bright days and genuinely dark nights. A planet where true total darkness was rarer, occurring only during the specific windows. When Centauri B happened to be below the horizon, might have shaped its entire evolutionary history slightly differently, favoring organisms and behaviors adapted to a night that was, on average, a little less completely dark than the one that shaped life on the real Earth. This is speculative, genuinely at the edge of what current science can confidently model, but it's a thread worth naming rather than skipping past, because it's exactly the kind of subtle, second-order biological consequence that tends to get overlooked in simpler versions of this thought experiment. There would have been a particular kind of comfort, too, in growing up with that second light always present, always there, regardless of season or weather. The real Earth's night sky, lit only by stars and an intermittently present moon, can feel genuinely, sometimes unsettlingly dark and empty on a clear, moonless night far from any city. A sky with Centauri B's steady, ever-present glow might never have offered quite that same experience of total cosmic emptiness. A small, easily overlooked detail, but one that touches directly on the deeper emotional and philosophical relationship. A civilization might develop with darkness, solitude, and its own sense of cosmic company. Winters, too, would have carried their own unfamiliar rhythm. With a year stretched to over 400 days, the coldest stretch of any given year would simply last longer in absolute terms, even if the underlying physical cause, axial tilt, distance from Centauri A, worked exactly the way Earth's seasons work today. Communities would have needed to plan food storage, migration patterns for any large animals dependent on seasonal change, and cultural festivals marking the depth of winter and the return of warmth, around a slightly different rhythm than the one actually embedded in human history and tradition on the real Earth. Not unrecognizable, just stretched very slightly, like a familiar song played a notch slower than the version you grew up with. We're nearing the end of this journey now, and it's worth taking one's last, deliberate step back to look at the full shape of everything we've covered, because the most important realization in any documentary like this one usually isn't found in any single chapter. It's found in the space between them, once all the pieces are finally laid out side by side. We began with a question that sounds almost playful. What if Earth orbited Alpha Centauri instead of the Sun? We end somewhere considerably more serious. Having walked through real orbital stability calculations, real habitable zone boundaries, real questions about lunar survival, real implications for the broader search for life around binary star systems throughout the galaxy, and real, ongoing observational searches for an actual planet that might right now be sitting exactly where this thought experiment placed its imagined one. Along the way, the deepest discovery wasn't really about Alpha Centauri at all. It was about home. It was about the quiet, easily overlooked stability of a single-star solar system. The kind of stability that never announces itself, never demands attention, never forces a civilization to develop of calendars accounting for a second star's decades-long heartbeat, because it simply isn't there to account for. Earth's actual orbit has remained close to its current gentle, nearly circular shape for an immense span of geological time, not because that was guaranteed by the universe, but because nothing nearby has ever seriously challenged it. That absence of challenge, that quiet astronomical good fortune, is so completely woven into the background of everything. Earth's billions of years of evolutionary history have produced that it took imagining the alternative. A planet, just one stellar address, over, in the very next system over, to actually notice it was there at all. That is, in the end, the real gift this kind of thought experiment offers, not a verdict on whether life could survive at Alpha Centauri, though the careful, evidence-based answer to that question. Plausibly, yes, under the right specific conditions, is genuinely satisfying in its own right. The deeper gift is a new way of seeing the system we already live inside, the one we've never had occasion to question, because we've simply never had anything to compare it against. There's something worth pausing on before we move toward the closing reflection, because everything in this documentary so far has been a careful, evidence-based thought experiment. But the system at the center of it is not purely hypothetical to real human science. Alpha Centauri is, right now, one of the most actively studied and actively targeted star systems in the entire field of astronomy, and it's worth understanding exactly what real efforts are underway, because they connect this entire thought experiment back to genuine, ongoing human ambition. several major observational campaigns, using some of the most advanced instruments available to modern astronomy, have specifically prioritized Alpha Centauri A and B as targets for direct imaging and planet detection. The technical challenge involved is genuinely extraordinary. Detecting a planet as faint and small as Earth, sitting incredibly close to an overwhelmingly brighter star from our vantage point, 4 light-years away, is roughly comparable to trying to spot a firefly hovering directly next to a powerful searchlight from across an entire city. Specialized instruments called coronagraphs, designed specifically to block out a star's overwhelming glare while preserving the faint light of anything orbiting nearby, represent one of the most active and rapidly advancing areas of modern observational astronomy, developed in large part because systems exactly like Alpha Centauri are considered such high-priority targets. Beyond detection efforts, there's also Breakthrough Starshot, a real, publicly announced research initiative, exploring the genuine feasibility of sending a fleet of extremely lightweight probes, each weighing only a few grams, equipped with thin, large sails, toward Alpha Centauri, accelerated not by onboard rocket fuel, but by an enormously powerful array of ground-based lasers pushing against those sails from a distance, in principle capable of accelerating the tiny probes to a meaningful fraction of the speed of light. Even under the most optimistic current projections, such a mission would still require a flight time measured in decades just to cross the 4.24 light-year gap, followed by years more simply waiting for any data the probe collected to be transmitted back across that same vast distance. The engineering challenges involved: building a laser array of the necessary power and precision, designing a probe and sail capable of surviving both the acceleration and the multi-decade journey through interstellar dust and radiation, maintaining the project's funding and institutional continuity across a timeline longer than most human careers, remain formidable, unsolved, and the subject of real, ongoing research rather than settled engineering. It's genuinely remarkable, against the backdrop of everything this documentary has covered, that the one-star system close enough for these kinds of real, serious proposals to even be worth discussing happens to be the exact same system at the center of this entire thought experiment. Every distance, every mass ratio, every dynamically stable zone calculation we've walked through across this journey isn't simply academic. It's the same body of research, directly informing real mission planning discussions happening in real observatories and real engineering labs today, precisely because Alpha Centauri occupies this unique, doubly significant position. Close enough to be the most plausible candidate for an eventual interstellar mission, and interesting enough, given its binary structure, to have already taught astronomers a great deal about whether multi-star systems can host stable, life-friendly worlds at all. In a real sense, by working through this thought experiment as carefully as we have, we've also been walking through the actual scientific reasoning that justifies why real human astronomers, real engineers, and real mission planners keep returning to this exact star system again and again as one of the most important targets in the entire search for understanding whether Earth's particular kind of cosmic good fortune is rare, or whether it's something the universe is capable of arranging more than once. Here's where the thought experiment touches something real enough to feel less like fiction and more like an open scientific question, waiting for an answer. For decades, astronomers have specifically targeted Alpha Centauri A and B in searches for actual orbiting planets, using some of the most sensitive detection techniques available. Tiny wobbles in starlight caused by an orbiting planet's gravity, minuscule dimming events caused by a planet passing in front of its star, direct imaging attempts using specialized instruments built to block out the overwhelming glare of the star itself in order to spot any faint planetary companion nearby. Alpha Centauri is, quite simply, one of the single most intensively searched star systems in the history of exoplanet astronomy, precisely because its proximity makes it the one place where these incredibly difficult detection techniques have the best possible chance of actually working. So far, no confirmed Earth-like planet has been found orbiting either Alpha Centauri A or B. There have been intriguing hints and candidate signals over the years. Tentative detections that generated real excitement among astronomers, followed in some cases by careful follow-up work that failed to confirm them. The normal, frustrating, essential process of real observational science, working exactly as it should. As of now, no planet has been conclusively confirmed around either star, though the search continues and newer instruments, some specifically designed with Alpha Centauri as a priority target, are actively working to either find one or rule one out, with much greater confidence than was possible just a decade or two ago. This detail adds a genuinely poignant layer to the entire thought experiment we've been building. We're not asking, what if Earth orbited a star system and completely ruled out as a candidate for hosting a planet like ours? We're asking the question about the one nearby star system, where the search is still actively, genuinely open, where real telescopes, right now, are looking for exactly the kind of world we've spent this entire journey imagining. If a true Earth-like planet were ever discovered there, orbiting Alpha Centauri, A, within the habitable, dynamically stable zone we've mapped out across this entire documentary, it would instantly become one of the most significant discoveries in the history of astronomy. Not because it would prove life exists there, but because it would transform every single calculation we've walked through from a thought experiment into a real physical world, sitting just over 4 light-years away, close enough that future generations of telescopes and possibly future generations of spacecraft might eventually be able to study it in genuine, direct detail. That possibility, however many further missions and decades it might take to resolve, is one of the quiet engines driving real continued interest in this system. We are, in a very real sense, watching the opening chapter of a search whose final answer nobody currently knows. It's worth pausing here to actually sit with the distance involved, because numbers like 4.24 light-years tend to slide past without really landing, and this entire thought experiment only carries its full emotional weight once that distance is genuinely felt rather than just stated. Light travels fast enough that it crosses the entire 93 million-mile gap between Sun and Earth in about 8 minutes. It would take that same light just over 4 years to cross the gap between our Sun and Alpha Centauri. That means the light arriving in your eyes tonight, if you happen to look toward that part of the sky, began its journey from Alpha Centauri roughly 4 years before this exact moment, meaning that everything happening on this very planet 4 years ago, every headline, Every personal milestone, every quiet, ordinary evening that has since been forgotten, was already in the past by the time that starlight even left its source. Now consider what that distance means for travel, rather than just light. Voyager 1, humanity's most distant spacecraft, launched in 1977, and now traveling faster relative to the Sun than any other human-made object in history, has spent nearly 50 years crossing a distance that, even after all that time, amounts to a tiny, almost negligible fraction of the gap to Alpha Centauri. At its current speed, Voyager 1 would need on the order of tens of thousands of years to cover the same distance separating us from Alpha Centauri, even though it's already farther from Earth than any human-made object has ever traveled. This is the brutal physical reality sitting underneath every version of this thought experiment on both sides of the swap. It doesn't matter which planet orbits which star. The 4.24 light-year gap between our actual Sun and the actual Alpha Centauri system is not negotiable. It is simply the distance, baked into the geometry of our small corner of the galaxy, and no amount of imagining a relocated Earth changes the fact that crossing it, for either civilization, looking toward either system, remains one of the single hardest engineering challenges either one could ever attempt. Real, serious proposals for someday sending a probe toward Alpha Centauri. Concepts involving fleets of tiny, gram-scale spacecraft pushed to a meaningful fraction of light speed using powerful ground-based laser arrays. Still describe one-way journey times measured in decades, even under wildly optimistic assumptions about future technology, even for the lightest, simplest unmanned probes imaginable. Sending humans with the life support, radiation shielding, and deceleration capability an actual crewed mission would require remains so far beyond current or near-future engineering capability that serious scientists generally treat it as a multi-century ambition, rather than something on any practical roadmap. So even in the version of this thought experiment, where Earth orbits Alpha Centauri instead of the Sun, the deepest, hardest question of interstellar travel doesn't go away. It simply points in the opposite direction. The relocated civilization wouldn't be dreaming about reaching Alpha Centauri, because they'd already be there. They'd be dreaming about reaching us, about crossing that same impossible 4.24 light-year gulf to study the modest, single, quietly stable star system, where, by sheer cosmic placement, real humanity actually got to grow up. Here's a thread worth following all the way through, because it touches something genuinely interesting about how a civilization's curiosity might be shaped by its home address. Real human civilizations' drive toward space exploration has always been entangled with a particular kind of restlessness, a sense expressed across centuries of philosophy, religion, and eventually rocket science, that there might be something more out there, that the universe surely couldn't be empty, that somewhere among all those countless points of light, there had to be other worlds, possibly other minds, possibly other versions of the same fundamental questions we've been asking about our own existence for as long as we've had language to ask them. A civilization growing up inside Alpha Centauri might have experienced a meaningfully different version of that restlessness, precisely because two of the answers to "Is there more out there?" would already, in some sense, be staring down at them every single night. They wouldn't need to wonder whether other suns existed. They'd be living proof of it, growing up under one. They wouldn't need to wonder whether stars could have orbiting planetary systems of their own worth investigating. Proxima Centauri, sitting at the edge of their own home system, would already be a confirmed, studyable example, close enough to send probes toward within a single civilizational lifetime, rather than requiring the kind of generational leap real interstellar travel demands. In a strange way, some of the deepest existential questions that have driven real human philosophy and science for millennia. Are we alone? Is our system unusual? Are there other suns with their own worlds? Might have arrived at this relocated civilization already partly answered simply by looking up. That could have reshaped their entire relationship with cosmic curiosity. Perhaps their restlessness would have focused earlier and more intensely on the deeper, harder questions. Not, are there other stars, which their sky already answered, but is there life on the world circling the dim red star at the edge of our own system? And eventually, what is actually happening around that quiet, modest, single star we can see far across the gap, the one without any visible companion of its own? Or perhaps, just as plausibly, having two confirmed suns and a confirmed neighboring star with its own planet might have made the universe feel comfortably full rather than achingly empty. Softening, rather than sharpening, the particular flavor of cosmic loneliness that has shaped so much of real human philosophy and religious thought across our own history. It's genuinely difficult to know which way that psychological effect would have actually tipped, and that uncertainty is, itself, one of the more fascinating unresolved threads in this entire thought experiment. We can model orbital mechanics with real confidence. We can calculate stable zones and habitable distances with real precision. But predicting exactly how a civilization's entire emotional and philosophical relationship with the cosmos would shift, given an objectively different sky, sits at the genuine edge of what any of this analysis can confidently claim to know. What we can say with more confidence is this: whichever way that psychology actually tipped the underlying physical challenge of reaching another star system, any other star system, would have remained exactly as forbidding for them as it remains for us. Two visible suns in the sky doesn't make the third one, the one 4.24 light-years away, any easier to reach. There's one more layer worth carefully unpacking before we begin pulling all of these threads together, because it touches something deeper than calendars or tide tables. It touches how a civilization might have come to understand the very concept of deep time. Real human science took an extraordinarily long time to accept just how old the universe, the sun, and the earth actually are. For most of recorded human history, dominant cultural and religious frameworks across the world generally assumed timescales measured in thousands of years, not billions. It took the careful, patient accumulation of evidence from geology, from the fossil record, from radioactive decay rates, and eventually from astrophysics itself, to drag human understanding of deep time from thousands of years to the genuinely vast, almost unimaginable scale we now accept. A universe roughly 13.8 billion years old, Sun, about 4.6 billion years old, an Earth of almost exactly the same age, life present on this planet for roughly 4 billion of those years, complex multicellular life only emerging in the last several hundred million, and our own species existing for a sliver of time so thin, relative to all of that, that it barely registers as a rounding error. That hard-won understanding came to real human civilization only recently, geologically speaking. Really only over the past 2 centuries or so, with the most refined modern measurements arriving within just the last several decades. A civilization raised under Alpha Centauri A and B, watching a visible companion star slowly orbit across the span of single human lifetimes, might have stumbled onto an intuitive appreciation for slow, vast timescales considerably earlier in their intellectual history. Watching an 80-year orbital cycle complete within a single human life is a genuinely different psychological experience than watching the sun trace the same yearly path it traced every year before. You were born, and every year it will trace after you're gone. The companion star's visible, trackable motion across decades would have offered a built-in, undeniable demonstration that the universe operates on timescales longer than any single human life. Sitting right there in the sky, observable, recordable, impossible to dismiss as mere myth or metaphor. Would that have meaningfully accelerated this relocated civilization's acceptance of deep geological and cosmic time? The same hard-won realization that took real human civilization so painfully long to fully absorb. It's impossible to know for certain, but it's a genuinely fascinating possibility, and exactly the kind of subtle second-order consequence that makes this entire thought experiment so much richer than its surface premise suggests. The shape of a civilization's sky doesn't just change what they see. It potentially changes how quickly and how naturally they come to understand their own place within the staggering scale of cosmic time itself. We've now walked through nearly every layer of this question, from the smallest practical detail to the largest philosophical implication, and it's worth taking a moment to assemble the full picture, because the individual pieces, on their own, don't quite capture how strange and how specific the final result would actually be. This is not a world of 2 blazing suns sharing the daytime sky, the way casual imagination often pictures a binary planet. That image, vivid as it is, doesn't survive contact with the actual orbital geometry of the real Alpha Centauri system. The true picture is quieter and, in its own way, more interesting. One true sun, Alpha Centauri A, providing essentially all of the planet's warmth and daylight, sitting close enough in apparent size and color to our actual sun that the daytime experience would feel only subtly different from the one we already know. And one extraordinary nighttime presence, Alpha Centauri B, bright enough to be unmistakable, slow enough to be tracked across a human lifetime, mysterious enough to have almost certainly shaped that civilization's earliest religious and astronomical imagination in ways our own single-sun sky never could. This is not a world doomed to chaotic, planet-destroying instability either, the way a more pessimistic intuition about binary star systems might suggest. The real research into Alpha Centauri's dynamical stability zones shows a genuine, scientifically grounded path to a planet maintaining a calm, life-supporting orbit for billions of years, provided it sits in the right place. Comfortably inside, roughly 2 to 3 astronomical units from Centauri A, and ideally adjusted outward to around 1.2 astronomical units specifically, to balance Centauri A's slightly greater brightness against the energy levels Earth's actual biosphere evolved to handle. But it is also not a world identical to our own in every meaningful respect. The year would run longer, somewhere over 400 days by our current calendar, demanding its own independent solution to the ancient problem of building an accurate agricultural and religious calendar. The deep time rhythm of ice ages and climate shifts. The slow engine that has shaped the entire evolutionary story of complex life on the real Earth would carry an additional, unfamiliar layer of gravitational interference from Centauri B's repeating 80-year approach. Not catastrophic, based on everything the stability research suggests, but different enough that the precise evolutionary path leading to a species exactly like Homo sapiens might never have unfolded in quite the same way, even given the exact same starting planet and the exact same starting biosphere. And it is a world that, almost paradoxically, would have made certain kinds of scientific discovery easier, and certain kinds of cosmic exploration psychologically different. The two-body problem of orbital mechanics, demonstrated visibly overhead rather than reconstructed through centuries of painstaking, indirect observation. A genuine red dwarf star, Proxima Centauri, sitting as a study-able neighbor within their own home system long before any serious attempt at true interstellar travel became necessary. A built-in, system-spanning proving ground for the kind of long-duration spaceflight engineering that any future leap toward another star system, including the leap toward our own quiet, single sun, would eventually require. Every one of these threads traces back to real, published astrophysical research into the actual Alpha Centauri system, the genuine mass ratios of its three stars, the genuine orbital period of the AB pair, the genuine distance at which Proxima orbits the inner pair, the genuine calculations researchers have run modeling where a stable, Earth-like planet could plausibly exist. None of it required inventing anything. It only required taking the question seriously enough to follow it all the way through, layer by layer, the way this entire framework has been built to do. There's a particular kind of realization that tends to surface only after a thought experiment like this has been pushed all the way to its limits, rather than left as a casual daydream. And it's worth naming directly, because it's arguably the most important thing this entire journey has been building toward. We started by asking what it would be like to live under two suns instead of one. We end somewhere quite different, with a clearer, more specific, more scientifically grounded appreciation for exactly how particular our actual solar system's quiet simplicity really is. It is easy, living on the real Earth, to take the single steady presence of our sun completely for granted. One star, one dominant source of gravity, one smooth, repeating, nearly circular orbital path, undisturbed by any nearby stellar companion's gravitational tug. One predictable yearly rhythm, refined and tracked by human civilizations for thousands of years, without ever needing to account for a second star's slow, decades-long heartbeat, distorting the math. It's the kind of stability so complete, so seamless, that it never even occurs to most people to wonder whether it could have been otherwise. But step inside Alpha Centauri, even just as a thought experiment, and that invisible stability becomes visible by contrast. A planet there, even in its very best, most carefully chosen, most scientifically favorable configuration, would still be living inside a system with a fundamentally more complicated gravitational story. Stable enough to support a real billion-year biosphere based on everything current research suggests, but never quite as simple, never quite as undisturbed as the system we actually call home. That contrast is, in the end, the real discovery sitting at the heart of this entire exercise. Not could Earth survive at Alpha Centauri, though the careful answer to that question, yes, plausibly, with the right orbital placement, is genuinely satisfying on its own. The deeper discovery is what that question reveals about the system we already live in, the one we never had to imagine, because we've simply always been standing inside it. Our actual sun's quiet, solitary stability isn't the default condition of the universe. It's one particular outcome among many possible outcomes the universe is capable of producing. A genuinely fortunate one, when measured against the additional complications a planet circling Alpha Centauri A would have had to contend with for the entirety of its evolutionary history. And yet, for everything this thought experiment has managed to pin down with real, careful astrophysical reasoning, it's worth ending, honestly, the way any genuinely rigorous exploration of a question this large eventually should. By naming what we still don't know, rather than pretending the picture is more complete than it actually is. We don't know with certainty whether a planet actually exists around Alpha Centauri A or B right now. In the real system, today, the search continues, genuinely open, genuinely unresolved, with better instruments coming online, specifically to settle the question one way or the other within the coming years and decades. We don't know, even in the carefully reasoned scenario we've built throughout this journey, exactly how the deep-time climate history of a relocated Earth would have actually played out across hundreds of millions of years. Only that current stability research suggests it would have remained broadly survivable, with meaningful but non-catastrophic differences from our own planet's actual climate story. We don't know whether intelligent life, if it ever did arise on such a world, would have developed anything resembling human civilization, human curiosity, human science, or whether the differences in calendar, sky, and deep-time rhythm would have nudged that hypothetical species down an entirely different cognitive and cultural path, unrecognizable to us in ways this documentary hasn't even attempted to guess at. And we don't know, despite everything we've learned about how close Alpha Centauri actually is in cosmic terms, whether humanity will ever actually close that 4.24 light-year gap and find out any of this firsthand. Whether some future generation of engineers, building on ideas already being seriously discussed today, will eventually send a probe, and after that perhaps something more, across the very same gulf this entire thought experiment has spent so much time describing from both directions. What we do know is this: the system next door is close enough, real enough, and well studied enough that asking what if we lived there instead isn't pure fantasy. It's a question with actual physics underneath it, actual numbers, actual published research, actual orbital stability zones that real scientists have calculated specifically because Alpha Centauri is the one place close enough for the question to matter. And somewhere in the careful, patient process of answering it, the thought experiment quietly turned itself inside out. It stopped being a story about a stranger, more complicated world over there. It became a story about the quieter, more fortunate world we've been standing on the entire time. The one circling a single, steady, unremarkable star, in an orbit so calm and so undisturbed that it took imagining the alternative to notice just how rare that calm actually is. There's a particular kind of gratitude that's hard to access directly, simply by being told to feel it. Nobody walks outside, looks at the sun, and spontaneously feels lucky that it happens to be alone up there, with no second star tugging at the calendar every 80 years. That kind of gratitude only really becomes available once you've done the work of imagining the alternative in enough careful, specific detail to actually feel the contrast. The longer year, the doubled night sky, the 80-year heartbeat running quietly, underneath every tide table and every ice age for the entire span of evolutionary history. That is, in the end, exactly what a thought experiment like this one is for. Not to prove anything decisive about another star system 4 light-years away, but to sharpen, by contrast, an appreciation for the one we actually call home. The sky above the real Earth tonight holds no second sun, no 80-year heartbeat tugging at the tides, no slow companion star demanding to be explained. It is, by the standards of everything we've uncovered tonight, a genuinely simple sky. It is also, very possibly, exactly the kind of sky a civilization needs, in order to have 4 billion years of undisturbed time to become something capable of looking up, noticing the quiet, and finally understanding just how much that quiet was worth. Somewhere out there, 4.24 light-years away, 2 stars are still locked in their slow 80-year dance, exactly as they have been for longer than human civilization has existed, exactly as they will continue, long after every name and every nation alive today has been forgotten. Whether anything has ever lived in the narrow, carefully balanced zone where their gravity allows a world to remain stable is still, honestly and without exaggeration, one of the open questions of our time. The telescopes are already pointed there. The calculations are already done. All that remains is the answer, somewhere out in that quiet 4 light-year gap, waiting to be found, or waiting, perhaps, to confirm that the particular, fortunate arrangement that produced everything we are, and everything we've ever built genuinely, was something the universe only managed to get right once, in this one small, single-star corner of an otherwise vast and crowded galaxy. That is where this particular journey ends. Not with an answer carved in certainty, but with a sharper question, a clearer sky, and a quieter kind of wonder about the stat that has, this entire time, been ours alone.